some mechanical systems and the mathematical model for them using differential equations. So from the physical law of the systems, we have developed the differential equations related to those mechanical systems. So we have taken, I think, three mechanical systems. Two of them are linear, and at the end, we have taken one nonlinear system. Now, today, we will start with okay, so I think this is visible to you.
Yes, ma'am.
Okay, so what we will do, we will see. I think in the last class, in the part A of this course, you have studied transfer function model.
Yes, ma'am.
Okay, so what we will do, we will start with the state space model of a system, and we will see the relationship and what are the things we can do with the state space model. As I'll assume that all of you have attended that class of the on modeling of systems using transfer function model, so that you can compare these two methods. Okay, so let's see. So in the last class we have discussed definition of system, why we are trying to model a system. Now let us focus on this. So from this, I think it will be clear that why we are so much into modeling the or mathematically modeling a system. The system, we can, what we can do, we can experiment directly with the actual system. In that case, we will not be knowing what are the limitations on the system. That is, what kind of input we can choose. Say, for the last in the last class we have taken a spring mass damper system as an example. So in that case, what are the limits on the inputs we should choose, or what are the limitation we should impose while doing an experiment on the actual system? Those things we generally don't know about a system. So therefore, it will be better if we can have a model of that system, and we can start our experiment on that model, so that we can have an idea that what to do and what not to do on the in the sense of what are the inputs we should provide to the system, or what are the what are the uh, uh, what are the ports from where we should take the outputs, or what should be the environmental condition while doing the experiment. Those things should be clear to the uh, user. So therefore it will be better to first experiment with the model of the system, and for that case we can go for a physical model of the system, or a mathematical model of the system. So a physical model will be, in the last class we have discussed that a physical model will be a can be in case of mechanical students, you have already told me that you deal with physical models of systems. In civil engineering also, it is more on the physical models of the system. But uh, in case of electrical systems, or in case of systems that are more uh, prone to analysis, that is like the prediction and mathematical analysis of the systems are prior requirement for the experimentation. In that case, generally we will go for mathematical modeling of the system. And from that mathematical model of the system, the first and foremost thing that we can do, if we have a very good knowledge about mathematics, then we can directly get an analytical solution of the system. That is, if you provide a particular kind of input, how the system will react, that you can analytically directly calculate if you can have a good mathematical model. Otherwise, what we can do, from the mathematical model we can go for simulating on that mathematical model, and from there we can have we can get the nature of the system. So therefore the simulation can be done in three domains mainly. One is in frequency domain, another one is in time domain, and a mixture of these two, that is a hybrid domain. Okay, so this is the purpose for which we are concentrating on this mathematical model of the system. So next, so in this course, what we will do, we will for this we will take the we will go for mathematically modeling systems, and we will try to get the idea of by simulation what we can comment on the system, or via simulation what are the things that we can conclude from the mathematical model of the system. That is our objective. So for that objective, towards that objective, we will take mathematical model of some mechanical systems, electrical systems, the combination of these two, that is some electromechanical systems, and hydraulic and thermal systems. Now, if we have these systems, how we can get the mathematical models of the system, that we can classify into uh, two broad categories. So here we will consider one category in which we can model the system is a transfer function model. That is, that will give us a input output relationship between the input and output of the system. And another one is the state space model, where we will get a idea about the internal the state of the components that are involved in the system. Okay, so we will discuss in detail. For the time being, just go through the outline. Now we will again see modeling of some nonlinear systems. In the last class, we have already seen the differential equation representation of a inverted pendulum system, and there we have seen that the differential equations involved for describing the system were nonlinear in nature. Okay, so this will be our objective. Now, in the last class, we have already seen how to, if you are given with the differential equation of a system, that is the differential equation representation is some kind of mathematical model of the system, then you can classify whether the system is linear or non-linear, whether it is static or dynamic, whether it is time variant or time invariant. These things we have already discussed. Now, the mathematical modeling can be of, but the type of mathematical modeling can be of three types broadly. That is, but in the approach by which mathematical modeling will be done, that can be of three types. One is white box method, and black box and gray box. What are these? So in case of a, the name itself suggests, see, white box model, that means the box, when the system is actually referred here as a box. So that means inside the box, if the box is white, that is say transparent, so that means you can see what are the components inside that box. So therefore the input, not only the input and output is not known to you, the internal dynamics of the system are also can be seen. So that means the physical laws involved to describe the system, that can be taken into account while modeling the system. So in the last class, when we have modeled the, say, do we have this? Okay, so in the last class, when we have taken this spring mass damper system example, so in that case, we were knowing the components of the system, that is the spring, mass, and damper involved. We exactly knew uh, the components, their interconnection, everything. Say this example we have taken in the last class now, so we knew the spring, mass, and damper, those are involved, and what were their interconnection. So that means this model we have taken in the, as a white box model. So all the components known, their interconnections known. Okay, so this is one kind of one approach by which we can go for modeling a system. Another one will be, another one is a gray box model, where we know we know some of the properties of the system and input and output to the system, some limited information about the system, that is the thing inside the box is known to us. So that kind of model is called a gray box model. Say say in a particular case, say if you know that there are these many components are there, but we don't know what is their interconnection, so that kind of model can be called as a gray box model. And the last one, is somebody is asking for permission, I guess. And the last one is the black box model. So in this case, only the input and output is known to you. So the system is considered as a black box. So we don't know anything. We don't know anything about this. What is inside the box? That is, what are the components involved in the system and what are their interconnection. So if we don't know, so then in this case, how we will model the system? If you only know the input and output of the system, say one method could be, can anybody suggest that if you know only the input and output of the system, can you suggest how will you model any method which is related to this black box model? Can anybody suggest? Nowadays everybody is working with data, na? Say you have a mechanical system or a electrical system where you are providing a voltage input, and at some port you are taking the output as another voltage, say, across across a component you are taking. So only the input and output is known to you. So with this v in and v out data, how do you model the system? Nobody. Okay, so I'll give you one example. So say there is a heat radiator that is placed near a furnace. So what we will do, we will capture the room temperature at different valve position. Okay, so at different valve positions, say at valve position 0, the room temperature is 0. So for 2 there is some room temperature is captured, and then for up to 10, at an interval of 2, we have taken the room temperature data. So now what we can do, we can have a card fitted through these points, and we can get a approx equation for this curve, and this equation will be a mathematical description of the valve. Do you agree?
Yes, ma'am.
So model fitting or card fitting, this is only one dimensional data, so therefore card fitting, if you have more dimensional data, you have to go for some other technique. So this is an example of a black box model. But in this course we are mainly interested in white box model. Okay, so we will assume that we know the system parameters, the components that are involved in the system. We know their system parameters, that means the values of the components that are involved, and we know the interconnection among them. So try to understand. So therefore I am saying that we are now onwards we are dealing with white box model of a system, and we are trying to get the mathematical model of a system for which white box means for which the components are known, the values of the components are known, and the interconnection among the components are known. So therefore we can go for mathematical model of these two types, that is transfer function model and state variable model, or we can go for some topological models. That is, topological model means we will represent the interconnection among them by some diagrams, and then we will try to extract the information uh, by reducing that graphical representation. Okay, so from here I am moving towards the state variable model of a system. So at this point I'll try to, if you can remember, you have studied the transfer function model of a system. In that in that kind of modeling, what are their limitations? Do you remember? Can you go for a mathematical model of this transfer function model of a nonlinear system? Can you derive the transfer function model of a nonlinear system? No, we cannot. So therefore, the transfer function model is actually limited to systems that are linear in nature and time invariant in nature. Not only that, the system should have one input and one output, and transfer function will give the relationship between that input and output in the complex frequency plane. And for that we will assume zero initial conditions. That means the component involved in the system that can store energy, like the mass or spring component, or the capacitor or the inductor, will not have any storage at the beginning of the analysis. Okay, this is the assumption for transfer function model. So these are some pretty high limitations on the system. So therefore, we are trying to remove these limitations by modeling it in state variable technique. So the state variable modeling does not require these assumptions. It can model nonlinear system as well as linear system. Sorry. It can handle zero initial condition. It is applicable to multi-input and multi-output system. Okay. So that's why this kind of modeling approach, the state space modeling approach or state variable modeling approach, is called the modern modeling approach. Okay. So why modern? Because that transfer function, it can include more. It is more inclusive kind of modeling, as it can handle nonlinear time varying systems as well, and it can take care of non-zero initial conditions. It can handle multi-input multi-output systems. So therefore it is considered as a modern technique. So what is the basic of this state variable model? So while we are considering this dynamical system, that means in the last 2 3 classes we have repeatedly we have discussed these dynamical systems. That means the output of the system is not only dependent on the input at that instant, it also dependent on the past inputs. So therefore the state therefore the dynamical system will have um, some variables that are able to represent the system at a point of time. That is, if we are talking about a spring mass damper system, so at the initial time, that is at t equal to t0, before applying any input, you need to know, is there any energy stored in the spring at this point of time? That is, before applying any force, you have to know whether the spring is already at a but already storing some energy or not. That is, already it is squeezed or already it is expanded. What is the state of the component that can store energy? Okay. So therefore, the property of the dynamical system is such that for a static system, it is not there. Okay, for a static system, this property is not required, as say for a static system there is no energy storing element. We have taken an example of a resistive circuit. Only resistors were considered in a circuit. If you provide a input voltage, you will instantaneously you will get a output voltage, and if you change the input voltage, instantaneously the output will change. Sorry. So therefore, the state of the system, sorry, the state of the system, state of a dynamical system is dependent on some set of variables at t equal to t0. T0 is considered as the initial time at which the input will be provided. Okay, the state variable okay, I'll come back to this slide. First, let us take one example. Okay, so the minimum number of state variables that will be required for describing a system will be equal to the order of the differential equation involved to describe the system. Say for a spring mass damper system that we have considered in the last class, uh, containing one spring, one damper, and one mass interconnection. In that case, what was the order of the differential equation? It was a second order differential equation involved to describe this system. And here you see there are two energy storing elements. One is the spring and the mass. So what was the state of this spring and the mass at the very beginning of the experiment, that is at t equal to t0? What is the state of spring and what was the state of this mass? Those are required for proper representation of the system, and the number of such variables, that minimum number of such variables that are required to describe the system, will be equal to the order of the differential equation. Now let's take this example. Say a system is described using this second order differential equation. This y double dot equal to, sorry, y double dot plus a1 y dot plus a0 yt equal to b0 vt, where vt is the input and yt is the output of the system. Okay, can anybody tell me, by seeing the equation, can you tell me whether this system is linear or not?
Yes, second order linear equation.
Second order linear equation, yes. So therefore, as we can see, the differential equation is of order 2. We can say that only two states will be required to describe the system. Only two states. Okay, so and we have the privilege to select the states. So you this state space, one thing you have to keep in mind, this state space representation is not unique in nature. Okay, in case of transfer function model, you have the input and output properly described. So the relationship between the input and output will be fixed. So therefore, the the transfer function representation is unique in nature. But in case of transfer function model, this is not unique. It is not unique. But there, it is not unique means you can have more than one representation, and all of them, if done properly, all of them are correct. Okay, so now after seeing this differential equation, the first thing comes that there will be two state variables involved. But what are those? So what are those? One choice could be this yt. You can take yt directly as a state x1 and y dot t as another state x2. And now I can write x1 dot. So what we are trying to do, we are trying to represent the system with the help of the states x1 and x2. There are two states involved here, and we have chosen them as x1 and x2. X1 is directly the output and x2 is the derivative of the output. Now I can rewrite this differential equation as x1 dot is equal to x2, and another one is x2 dot. X2 dot means y double dot. X2 dot is equal to minus a0 x1 minus a1 x2 plus b0 vt. Is it okay?
Yes,
Now,
ma'am.
now we can rewrite this as in a matrix form, where x1 dot t and x2 dot t is stacked in a array, which is actually the derivative of this array x1 and x2. If you take these two states stacked in a array, this is the derivative of that array. Okay, so now we can write, you see here, x1 dot is equal to 0 x1 plus 1 into x2. That is x1 dot is equal to x2, this representation of this equation. And the second one is the representation of the second equation. And what is the output? The output is actually x1. So therefore we can write yt is actually this matrix into this one. Yt is equal to x1t. Is it okay?
Yes, ma'am.
Now, now, oh, this is, now you see, we can now represent this x1 and x2 as a vector. This is called the state vector. So in general, there could be, for say, for a system represented with, or a system having n number of energy storing elements, will be of will require nth order differential equation, and in that case the state vector will have n components, x1, x2, xn. So this is the generic representation of a state vector, which will include all the states stacked in an array or stacked as a vector. So this is odd x, and this is a matrix which will be relating the derivative of the state vector with the state vector. So this is actually responsible for the dynamics in the system. Therefore this is called the state matrix or the dynamics matrix. Okay, this 0b 0b0, this is called the input matrix. Why? Because this relates the change in states with the input. So this is called the input matrix or input vector. In this case this is vector because there is only one input, but please note that if there are more than one inputs involved, in that case this is also will be of different order. Do you agree?
Yes, ma'am.
So therefore it will be a matrix, and this C is the output vector or output matrix. In this case it is vector, but in general it could be a matrix because there could be more than one outputs involved. So if there are more than one output involved, then this will take a form of a matrix. Say there are two outputs. If there are two outputs, then we will have the C matrix as a 2 cross 2 in this case, as there are two states. So in general what we can write, this is our state space representation. Sorry, this is our state space representation, where the first equation is called the state equation or dynamical equation, and this one is the output equation. This equation involves the change in the state. The change in the state is represented by a function of the state as well as the input. Okay, the change in the state is represented as a function of the state and the input. And this is the output equation, which is, in general, here we will have another term, that is dv. Cx plus dv, that is the output, can also be represented as a function of the state and input. Okay, for the example we have taken, there is no D matrix. You can consider D matrix as 0 for this example taken into account, but in general the representation is like this. Okay, so for a linear system, this state space representation is actually a matrix representation. And if you go for analytical, so the purpose of the mathematical model is actually to analyze the system. So for analysis, only knowing matrix, this linear algebra, that is the analysis of matrix, you can analyze the system. This is the advantage. So from a dynamical equation, you have broken it into a representation of matrix. So by analyzing the A matrix only, you will have so many information about the system. Okay. So this is the purpose. Now next let us see. So therefore, let me go back to this slide and try to understand in this respect. So therefore, see in this case, you have to we had a second order differential equation, and for that had to choose two state variables. So we have taken the output directly as a state and the derivative of first derivative of the output as a state. You could have taken something else. So the first step is to choose a choose the set of state variables, and if it is a nth order system, then we have to choose n such variables, and next we need to write n simultaneous first order equations. Okay, do you understand first order equations? This, see in this case, say in this case it was a second order differential equation. In the first step we have chosen the states, and then we have written the differential equation, we have rewritten the differential equation as a set of two simultaneous first order differential equations. You see, only first order differential equations are involved here, although it will take care of that nth order differential equation, because you have already taken n such states, and the derivative of those states only will give you the whole dynamics of the system. Okay, now next we will write a output equation, which is a algebraical combination of the state variables. That is the C matrix we need to write, and these two equations, the state equation and the output equation combined, will represent the state space representation of the system. Now let us take a example of a RLC circuit. Here, let us first take a RC circuit. So here, here we are providing an input V in here, and through this RC circuit we will only measure the output voltage across this capacitor. Okay, so for the application of the input voltage V in, there will be a current I flowing through this loop, and we will take the voltage across this capacitor as our output, or this is our point of interest. So this is V out, we will take as output. So now one state space model could be that you directly, so how many energy storing elements are involved in this system? Can you tell me what are the components R and C? So among these two, what which are the components that can store energy?
The capacitor.
Only the capacitor. So we have only one energy storing element involved, so we will have to choose only one state. Okay, so one choice could be that you take the V out directly as a state, the voltage across the capacitor as your state, that whatever is the voltage across the capacitor, I'll choose it as the state x1. So therefore we can write that uh, the current flowing through this will be current flowing through, you can write as C This d v out, this is, so that's why it is written as dy dt, and dy and this is actually equal to sorry, this is actually equal to current flowing through this resistor, which is v in minus y by r, the voltage drop across the resistor, that is v in minus y by r. So this is rewritten as this, and then we get this, that dx1 dt is equal to minus 1 by rc x1 t plus 1 by rc v in. So derivative of the state is related to the state and the input. So this is the state equation. So therefore x1 dot is equal to minus 1 by rc. In this case we are getting only one element in the matrix, that is there is only one state involved, so the order of the matrix is 1 cross 1, and this is our input matrix, and this is the output matrix. Okay, so now can you tell me, if say I'm saying that the for the state variable model I have this state matrix, the order of the state matrix is actually the state matrix actually belongs to Rn. Do you know the meaning of Rn? That means the X matrix will have n components. The state vector will have n components in it. That is, sorry, X is actually x1, x2, like that, xn. Okay, so can you tell me, if there are n elements in the state vector, then what will be the dimension of A matrix? Sorry. What will be the dimension of A matrix? A matrix relates the derivative of the x vector with the x vector. Do you agree? So the dimension of x dot will be always equal to dimension of x. If the x matrix is having n elements, what is the order of this? What is the size of the matrix? N cross 1? Yes or no?
Yes, ma'am.
So then what will be the order of this A matrix? What will be the order of the A matrix? It will relate a n cross 1 matrix with another n cross 1 matrix. So what will be the order of the A matrix? The derivative of this matrix Derivative of this vector is related to the original vector. This is n cross 1. And say there are m inputs involved. Say u1, u2, um. So the input matrix is m cross 1. So now you tell me what will be the order of this A and B matrix. You understand the question?
One into n and b also one into n.
What?
M into
One
n.
cross n.
M into n.
See, this x1 dot, we will get x1 dot by multiplying one row of this A matrix with this vector plus one row of this B matrix with this vector. Do you agree?
Yes,
So
ma'am. So it
x1
will.
dot we will get with this one row of A matrix multiplied by this x vector and one row of this B matrix multiplied by this
Yes, ma'am.
U
So it will be
vector.
n into n. N cross n.
So
N cross N.
always this A matrix will be a square matrix and
N cross N.
it will depend on the order of the state matrix or order of the state vector. And what will be the order of the B matrix?
N cross M.
Obviously, so matrix multiplication where output is already given by this n. Na? so so we will have. And what about this output matrix? Say if we have p number of outputs, say y1 and yp, y1, y2, y3, like that, p number of p into 1. This is the dimension of output matrix. Then what will be the dimension of C matrix? Can you tell me? X is n cross 1. What will be the order of C?
P cross N.
P cross n. So therefore, you see, this is the generic representation of the state space model for linear system. For a linear system where what will be the order of this? This will be P cross M. Okay. So this is a generic representation where you can see that a state space model is equipped to model a multi-input, multi-output system. Because here we have considered multiple inputs, y1 to ym, multiple inputs, y1 to y1 to yp, multiple outputs. So unlike the transfer function model, this representation is capable of
Ma'am, it will be
representing
n cross p or p cross n.
which one?
The order.
Order of what?
I think it will be uh, n cross p.
Order of
P
C.
cross
C
P cross
matrix.
N will be there. Otherwise, multiplication will not be possible.
C matrix, see the first element, that y1 you will get from the multiplication of the first row with this. So in the first row, how many columns should be there? N columns? No.
Yes, ma'am. Okay, okay.
So like that, you should have p rows. So therefore, p cross n will be the order of the C matrix. Okay. So if you have multiple inputs and multiple outputs involved in a system, this representation, mathematical representation, is capable of taking care of that system. Okay. So now let us move to, if you have any problem, please ask. Huh? This is online mode now. We cannot, I cannot understand what is the. This is a simulation of the class. This okay. So let us take another example. Let's see. Okay, let us take another example of a RLC series circuit. Why we are taking RLC series circuit? Because here there will be more than one energy storing element, so that you can have an idea of that matrix format. In the last example, it was only a scalar representation. There was no matrix involved. No. So here you will have a similar representation, only we will take the output, that is, say, so this is the description of the physical system. We are taking a white box model, therefore we know there are RLC are the components, and this is their interconnection. So therefore we can write the input voltage V as the summation of Ri plus L di dt plus 1 by C integration of I dt. Okay, now what are the energy storing elements involved in this system? Energy can be stored as,
Inductor and capacitor.
yes, so as charge in the inductor and as,
It filled in capacitor.
yes, so as magnetic energy in inductor. So
Sorry,
therefore,
in inductor.
yes, so therefore we are taking, we can directly, what we can do, we can see, if the physical model is known to you and you have a very good idea about the components, then you can directly say, one can say that the energy stored in C will be equal to the charge.
Yes.
So it will be the proportional to the charge that is stored in the capacitor. So one can directly take Q as one state. Q, that is a charge. So Q actually means, current means the rate of change in charge, na. So therefore one can take the state of the states that are involved to describe the system, that are the energy stored in the capacitor and energy stored in the inductor. So one is directly proportional to Q and another is directly proportional to current.
Yes, ma'am.
Okay, so that's why I have taken these two. What you can do, say you are we are so we will take the voltage across the capacitor as our output. So you can follow the first method, that one state I will consider as the voltage across the capacitor, and the derivative of that voltage we will take the second state. Okay, so this state space representation is not unique. So the selection of states is entirely your choice. And if you follow the proper methods, and the choice is yours, but after that you have to follow a proper method, then you will that is a, you will get a state space model that is true. So this model is not unique, and you can have more than one, you can have many this representations. So one of the representation we are taking a state x1 as q and x2 as derivative of q, that is the current. Why I am taking this? Because we have a very good idea about the system. So say for a spring mass damper system, I'll always take the velocity as one state and position as one state. Why? Because I know that the energy stored in the spring is directly proportional to the position, and the energy that is the energy stored in the mass, that is proportional to the velocity. That will be half mv square, and that will the energy stored in the spring will be half kx square. So therefore I can take x and v as two states. Okay, if somebody takes other than that also, or any linear combination of these two.
But we have to measure that particular property, I think, because in
Yeah,
this
that's
case,
why I am saying, see in this example, say in case of this, model, I didn't know what was the model about. I don't know whether it is a spring mass damper system or RLC circuit or
very first,
some other system. So what we have done, we have taken some choice, that is the output. This is the input output relationship, na? One differential equation representation of the input signal and the output signal. So I choose the I chose the output as a state and the derivative of the output as another state. So for a nth order system, you always have this choice, that you take yt as one state, y dot t another, y like y double dot t another state, like that, yn minus t as your nth state.
yes, ma'am.
So that is one choice, you can go for that. Now, as we have some idea about these systems, we are taking like this. That is why we are privileged to know this system. Okay. Now
Ma'am,
let
if
me. Yes.
the order of the equation gets increased,
Hmm?
then obviously the number of the state variable will also increase.
Obviously, the
So
number
in
of the
that
state
case,
variables is equal to the order of the dynamical equation.
we have to measure suppose there are n number of the state variables, so we have to measure n number of property to solve that state variable model.
No, you don't have to measure. See, this is we are trying to get the mathematical representation of the system. You don't have to measure anything at this point of time. If you have the mathematical model, you can analyze if this type of input is given, what will happen to the output. You get
Okay,
it?
so we don't have to put any boundary condition.
What are the boundary conditions that you will be able to find if you get the mathematical representation? You
Yeah,
see,
suppose there are n number of solutions,
in
then
this case, when we have got this mathematical model for this RC circuit, you got this relation, that is, this is the A matrix minus 1 by RC.
yeah,
You know the values of R and C. So the mathematical, say 1 by RC is equal to zero point 0.5. So what you get is the change in the state, that is the change in this V out voltage, will be minus 0.5 into xt plus 0.5 into vt. So now you can simulate that if you provide a input of this amplitude, how this xt will change. You get it?
yes, ma'am.
So this is the need for the mathematical model, that without knowing or without measuring or without experimenting on the system, you can get a
Yes,
analytical solution for the system first. then you
Yes.
see then you see that for these components, maybe say if you cross the input level beyond this, the system circuit can get damaged. So that information also this mathematical model will provide. So after that you go for experimentation.
Yes.
Hmm. Okay, so let us move to the next example. Here we will have a second order representation of this series RLC series circuit, and from there we will we can we can uh, represent them using, sorry, we can represent it using simultaneous first order equations like this. So x1 dot, so this is in two different pages, so that will be a problem. Otherwise you can this is very easy, you can see from this that we will try to represent this x1 dot is actually x2. So we will write x1 dot is equal to 0 1, then x1 x2 plus 0 vt. So x1 dot is actually x2, and x2 dot is x2 dot will be found from this equation. Okay, so x2 dot can be represented like this. So we have a matrix which is 2 cross 2, a B matrix that is 2 cross 1, and a this output matrix C matrix which is 1 cross 2. And here you see there is a D matrix. There is a D matrix involved which is V. Okay, now by analyzing, so I hope you all know the eigenvalue eigenvector analysis of a matrix.
Yes, ma'am.
Mhm. So only by knowing uh, the eigenvalue analysis of this, only by knowing the matrix analysis methods, we will be able to analyze the dynamics of the system. Okay, so um, this same example, this is that RLC series circuit, I have taken another choice of the states so that we can see that this is not unique in nature. The state space representation is not unique in nature. Okay, so what we will do, if you have gone through the this transfer function model, you will be able to uh, relate to this equation. That is, this is the transfer function representation of the spring mass damper system, where we are taking the V out as the voltage across the capacitor, and this is the relationship between this V, sorry, what is this? Achha. So this is the relationship between this voltage across the capacitor and the input voltage. This is a transfer function of the system. Okay. Now somebody is asking for, so let us see. Okay, so this is the transfer function representation. Now, as I have told you that as VC is the output to the system, output of the system, no, VC is a voltage across the capacitor, and that is the output of the system. I can assume one state as the voltage across the capacitor x1, and another state is the derivative of the output. Okay, so this is another choice. So by this choice I get the state space representation as this. Okay, you see the two state space representations are different. For the same system, this was one representation where we have this Y matrix as 1 by C minus 1 by C minus R, and there is a D matrix present. A matrix is this, B is this, C is this, and D is this. This is one state space representation of the same RLC circuit. And this one is another representation. You see? You see? The A matrix, B matrix, C matrix, and D matrix all are different.
Yes, ma'am.
But these two representations are for the same system. Okay. So people who have good idea about, okay, let me go to the next. So therefore, say one thing you have to keep in mind, that this state space representation is not unique, but it should map to the same transfer function model, na? The transfer function model is unique. So therefore, all the state space representations that you are getting for a system will map to the same transfer function model. So let us see how we can get the conversion, that is the relationship between the transfer function model and the state space model. So this is the relationship. What we will do, this is our state space model where x dot equal to ax plus bu and y is equal to cx. So if we take the Laplace transform with, say, this representation didn't have the assumption that it is with zero initial condition. It can handle initial conditions. Okay, but if you have to find the equivalent transfer function of this model, so therefore you have to take the assumption that there is zero initial condition. Do you agree? Because transfer function is only valid for zero initial condition. So therefore we will take the Laplace transform of this equation, the first equation, the state equation of this equation. We will take the Laplace transform of this equation. So we will get actually s into xs minus x0 we will get, na? So zero initial condition means we will put x0 equal to 0. And therefore we can write xxs. Do you agree? Please respond.
Yes, ma'am.
It is difficult. Okay, so now we can write xxs equal to axs plus b vs. Take this xs this side, and then you will get si minus a into xs equal to b vs. Okay, so next we will get xs as si minus a inverse b into vs. Why this I is required? Can anybody tell me? From this, why we are writing si minus a?
Because ma'am, A is the vector as to
A
represent
is the
as a
matrix. So if
it's a
the
matrix. Yeah.
dimension of x is n, so then A will be n cross n in nature.
Yeah.
So therefore, you will
I will be in number, I mean, identity matrix of order n.
N cross n identity matrix. So therefore, we can now write xs as Si minus A inverse B Vs, and y can be written as C into xs, which is C into Si minus A inverse into B Vs. And you know that transfer function is actually the ratio of Laplace transform of the output with the Laplace transform of the input. So therefore, ys minus ys by vs can be represented as C into Si minus A inverse into B. Okay. So therefore, if you find the transfer function of any system which is having more than one input or output, say now one thing you see, if it is a nth order system, that is there are n number of states, that means A matrix is n cross n. If there is only one input, what will be the order of B? B will be already discussed. We have already discussed this one, I guess. No, where is this? See, if it is the state number of states are n, then A is of n cross n order. If you have only one input, that means B matrix will be n cross 1. If
Yes,
there
ma'am.
is only one output, then C matrix will be 1 cross n. Do you agree? So if we are talking about C into Si minus A inverse into B, that means this Si minus A inverse is actually n cross n. C is 1 cross n. B is n cross
N
1.
plus
So therefore, it is a 1 cross 1
2 matrix.
representation. If there are more than one input and more than one output involved, then this transfer function representation will be a transfer function matrix representation. That is a matrix that will have elements that are transfer functions. Okay.
Yes, ma'am.
Okay, so let us move to this. So this is the transfer function representation of the RLC circuit. So what you can do, I have given you these two representation of the same system. Na? Say, let us name them. For the RLC circuit, we have the first representation. We can call it A1, B1, C1, and D1. And the next representation is A2, B2, C2, D2. And they should map to this same transfer function representation. So therefore, what I am suggesting is you please verify this. So we had two representations. We had two representations of the same system. One is with A1, B1, C1, and D1. Another one is with A2, B2, C2, and D2. Maybe D is 0, but there is D2. No? So now you verify that if you find the transfer function, which is actually equal to Ci into This I suffix I am writing for the different representations. You can have 1, 2, 3, 4, so many representations of the same system. So Ci into Si minus A inverse into Bi plus Di. This is the transfer function equivalent of a state space representation. So if you put 1 here, so that is C1 Si minus A1 B1 D1, you will get the same thing. And if you put 2 in place of this, you will get the, it will map to the same transfer function model. Please verify it for yourself. Okay, so this can be actually, people who are good at matrix algebra can tell me what is the, why it is happening and why there will be infinite a number of options. Can anybody tell me? Can you tell me? Can you think about it at least? Say actually the new state, say we are talking about a state matrix with different choices of states, na? Say a system is having two states, x1 and x2. Somebody else is taking the state variable as a combination of two different variables. I am taking a state. So what we can write is, this is actually can be written as a linear combination, that is some matrix multiplied by x. Do you agree? These choice of states can be transformed from one to another, and therefore it will actually be a similarity transform. This will result in a similarity transform. So therefore you can have, if you are interested I can calculate that. If please let me know if you are interested, then why it is happening we can discuss. Okay. Okay, so in today's class what we have discussed is, we have discussed the preliminaries of the state space model. We have taken some examples to explain the state space model, and then we have seen that the state space model is capable of eliminating the limitations that are found in state transfer function approach. That is, it is not limited to CISO systems, it is not limited to LTI systems, and it can handle non-zero initial conditions. And we have also seen the relationship between the state space representation and the transfer function representation. Okay, if you have any question you can ask, otherwise we will end the class here. Do you have any question? So let us conclude the class here.
Okay, ma'am.
Okay.